Alright, hi everyone. We're going to do arc length and surface area of a planar curve. Planar curve, remember, means it comes from a parametric uh, equation. So first off, arc length just comes from our idea of what we did when finding speed in the previous video, because speed was just the length of a hypotenuse. Well, what we do is we imagine those lengths get really small and we add them all up in an integral. So it's kind of like our speed thing, but we're just going to do an integral of it and it adds it all up. So I would like you to write the starred thing down. So this is our formula for doing the length of a parametric curve, or a length of a planar curve. So you've got your x component derivative squared plus your y component derivative squared, square root, and then just whatever your integral values are. Now this works as long as the curve is smooth and it's not intersecting itself, other than at the endpoint. So it could come all the way around and then re-meet at the endpoints, and that's okay. So I'm going to keep going again. If you need to pause at any point to write the formula down or whatever, feel free to do that. So you don't necessarily have to write the examples down, because you'll have these videos as a reference as you're doing the homework problems. So if you want, you can just follow through them, but the starred stuff I would like you to have written down in your notebooks. All right, so we want to find the length of our planar curve from 0 to pi. So we'll take the derivative of our x part, negative 4 sine t, derivative of the y part, 4 cos t. So we'll have integral from 0 to pi. We'll have our x part squared, so we get 16 sine squared t, plus our y part squared. Well, notice if we pull out a 16, sine squared plus cos squared is just 1. So this becomes just 4. Antiderivative 4t, sub in, you get 4 pi. So that's not too bad there. So a little more challenging example. So say we've got a circle, radius 1, and it's rolling around the outside of a larger circle that has radius of 4. And we want to know the path of a point on the outer edge of the circle. And the x and y coordinates are given by this. So just so you can get a visual of what's going on. So here's that idea. Okay, so we're tracing something on the outer edge. Now the one difference is this particular example, the outer circle has a radius of 1, and here the bigger circle has a radius of 3. That's why we end up getting 3 sections. Well, in our example, we have a 1 to 4 ratio, so we're going to end up getting 4 sections. So our picture would look kind of something like this, where we get 4 sections. Well, remember, we can only do arc length if it is smooth or it doesn't intersect itself. So only that first quarter is smooth, but then we've got like that cusp there. So what we have to do is we have to do the arc length just for that first quarter and then multiply it by 4 out front. So this was our x part. So if we take its derivative, we get negative 5 sine t plus 5 sine 5t. And similar idea for the y component. So we'll have the x component squared plus the y's derivative squared all in the radical, going 0 to pi over 2, because that's the section that's smooth, and then we just put a 4 out front. Now for this particular one, we could just put it in the calculator, and it would give us 40 back. So if you could write that equation down. Actually, you can write both of those down if you want. So we saw in Unit 5, when we were doing like disc shells and washers, we then also did surface area. And surface area was 2 pi radius times the arc length, all in an integral. So it's pretty much same idea here. So notice that radical part is the arc length that we just did. And then the radius, depending on which axis we're going over, if we're going around the x-axis, it will be our y part of our equation. And if we're going over the y-axis, it would be the x part of our equation. So again, if you need more time to write those down, you can pause it, but I'm going to move on. So say we want to find this curve spun around the x-axis, and we want to find the surface area. So we'll have 2 pi. Our radius would be the y component, because we're going around the x-axis, so the 3 sine t. If we take the derivative of our x part and the derivative of our y part, square them and add them together, we get this. And that's our arc length portion, and we're going 0 to pi over 3 for our t values. So if we pull out a 9, that'll leave us with sine squared, cos squared, so that part's 1. This part is 3, so this 3 and that 3 gives us 9, times the 2 pi would give us 18 pi. Then we've got a pretty simple antiderivative, negative cos t. If you fill in the pi over 3, that's really just 60 degrees, so cos, we would end up getting a negative 1/2, and then cos of 0 is 1, so that would be minus a minus, so you get positive 1. So that half times 18 pi would just give us 9 pi. So be on the lookout for pulling something out in the practice problems and being able to use that Pythagorean property to get it to be 1. And if we looked at the same curve, but now spinning around the y-axis, the only thing that's going to change is that radius. The radius is now the x component. This we saw a second ago was 3 because of the Pythagorean property and the square root of the 9. So now 3 times 3 is 9. That goes out front. We'll have antiderivative cos to sine. 60 at pi over, or at sine at pi over 3 would be square root of 3 over 2. 0 would be 0, so we get 9 radical 3 pi. Alright, so that's it for arc length and surface area. Remember, it can be done on only a smooth part, so sometimes you might have to put a number out in front and just do the smooth part. And if you're unsure if it's smooth or not, remember you can just graph it as a parametric function in your calculator and take a look at it. So do the practice problems that are listed under the task on Schoology.